Hi there. Today we are going to talk about transformations. I'm Vivek Subramanian.
And I'm Michel Maharvaz. Let's get started. So first, let's have a little reminder about independent sources. This will be very brief, just to refresh something we've already told you. So a voltage source, which we've looked at before, an independent voltage source, is essentially something that sets the voltage drop across two nodes, shown here. And it also tells you the polarity of the voltage drop Vs. Okay, so these plus and minuses have a meaning. We often draw the symbol slightly differently if we intend to convey the information that it's a battery. But in our course, honestly, these two things are kind of used interchangeably. Now, let's look at what this means on a plot of current versus voltage, so-called IV relationship or IV plot. So that voltage source, when we plot it, looks exactly like this red line. And really, this is telling you what I just said in English, that no matter what the current that may be flowing in either direction, whatever current is flowing between these two nodes down this branch, the voltage will stay at this value here, which is Vs in the case of this voltage source. It's always just going to sit at this. And thus, you have a vertical line. A current source is going to be the dual of this. So a current source always sets the current. And in this case, the arrow tells you that the positive current IS is flowing from this node up to this node. That's the direction of the current. So this means something, this arrow. And if you do that plot, as you can imagine, that this value IS, which is the value on the y-axis here, is going to be maintained at exactly that value, no matter what the voltage that may arise between this node and this node. Okay? And that's really a very simple observation, but it helps you graphically kind of come to terms with what these things are doing within your circuit. Now, you can imagine that a resistor, because of Ohm's law, the voltage across a resistor V is equal to I times R. Thus, basically just bring the I over. The 1 over the slope of this line, because I is on the y-axis and V is on the x-axis, the slope of this line is going to be 1 over R.
It's worth pointing out that these sorts of IV plots are things that we often make for all sorts of components. So on this plot, you see one for a voltage source, a current source, and a resistor. We can generate these sorts of IV plots for all the types of electronic devices that we use.
That's right. And it's both useful for getting an intuitive feel of how it works. You can see maybe a nonlinear device, which would have some strange characteristic in an IV plot. And it also, in some cases, is a quick tool for finding the solution of how a couple of devices together might work, because you can graphically plot both of these things and look for, say, intersection points. But that's something we'll cover later in the course.
Okay. Now, so far, Michel has been talking about ideal sources, but as a reminder, previously we introduced the idea of realistic sources. And real voltage sources always look like an ideal voltage source with a resistor in series. Now, let's remind ourselves of a real-world example of that. You remember when we talked about how you start a car. Let's say you have your headlights on your car, and then you turn the crank to start the engine.
Okay.
The light dims briefly.
Oh, that's right, yeah.
And the reason the light dims is you're pulling more current when you're trying to start the car, which lowers the voltage on the battery, which causes the light to dim.
Okay.
So why does that voltage go down? It goes down because there's a series resistance associated with that battery. When you pull more current...
Oh, I see. You're saying that let me see if I understand. You're saying that there's effectively a resistor here. And so when you pull some current, the actual voltage on this is going to change from the base voltage? Is that what you're saying?
Correct. What's going to happen is we have a load sitting over here,
yeah,
which let's model it as a resistor for now.
Okay.
So we have a load sitting over here, and the normal load is the load of the headlight, and so there's a certain voltage that appears across the headlight because this is a resistive divider.
Right.
Now, when I turn the car on, or I attempt to turn the car on, suddenly there's even more current attempting to be pulled over here, and that means, current continuity says that the same current is flowing through the entire circuit, so there's a larger voltage drop over here, which means the effective voltage you see on these terminals has now gone down.
Okay. That's interesting.
So that's what a realistic voltage source looks like. And so all realistic voltage sources are modeled as voltage sources with resistors in series. Current sources, on the other hand, we model as current sources with resistors in parallel. Now, the reason we do that is fairly straightforward. Michel just told you that the current through a current source is fixed. if the current through a current source is fixed, one way to make it give effectively less current is to use current division, which we learned about in the last set of lectures, to shunt some current away. And that would be a resistor in parallel.
Okay, so what you're saying in the bottom case is that that resistor RS is modeling the fact that not all the current from that IS source gets out to whatever the source is driving. Some of it is lost by whatever method into heat within the system itself.
That's exactly right.
That makes sense. Okay, and that's RS.
And that's RS.
Yeah. Okay, works for me.
Now, what we should talk about next is how to convert from voltage sources to current sources for the purposes of our calculations. Before we do that, remember that we talked about equivalent circuits, and so this is going to be our first example of generating some sort of equivalent circuit.
Yeah, and I think it's actually a pretty neat thing to observe. So, consider this circuit we've got here on the right. We've drawn an ideal voltage source here with its resistor. So together these things form a realistic voltage source. And they're connected to some external circuit. And we don't know or really care what's in here, but we do know that the current going into it down this branch is I, and we know that the potential drop or the voltage drop between node 1 and 2 is V12.
So you're saying that the voltage seen by the external circuit is V12.
That's exactly right. And this gets to, for example, your headlight example when you were talking about what this voltage is. But just, from this circuit and giving this, whatever the voltage drop may turn out to be, giving this a V1 label of V12, we can write a KVL equation. And so starting from the bottom left and following what we taught you last time, we're going to write a KVL equation that is minus Vs, right, as we come up to here, plus I times R1, you can follow along on the left here, plus V12. And then it brings me back down to this node, and I'm done. And that equals 0, okay? Now, I can rearrange this a little bit very simply to solve for I. So I'm curious, what is the current I? And I know that this current I is the I that's going into the external circuit, right? Because there's nothing else that's drawing off I, drawing off current. So I is going to be Vs divided by R1 minus V12 divided by R1. Okay?
And you got to that just by rearranging that
That's
equation.
all I did, yeah. Okay, so now let's look at a slightly different circuit. What if instead of driving this external circuit with a realistic voltage source, I drove it with a realistic current source? And I kind of did the same, I looked for the same expression. So in other words, let's just take a second. Here I have this ideal current source IS. It's driving this current I. I have a resistor R2. And so this current IS is going to be split. Some current's going to go down R2, so we'll call that IR2, and some current's going to go into the external circuit. So notice right away that this current I that's going into the external circuit and this current I that's going into your circuit are labeled the same way with the same symbol for a reason.
And I assume that one of the things you want to do is, for the purposes of this sort of equivalence analysis that we're doing, you're going to want R2 to equal to R1?
Well, let's not get there yet. You're jumping ahead. Let's see what happens just by trying to equate them. How about that?
Okay.
So let's say I don't know anything yet about R1 and R2. So just from this circuit, let's solve for I, just like I did up here. Up here I asked, what's the current going into this external circuit? So what's this current going into the external circuit? Well, it's pretty easy by KCL, right? So IS is going to equal IR2 plus I, right? Because this node, right, all this current coming in has to equal these two currents. So I, by rearranging, I get I equals IS minus IR2, right? Just KCL. And I know what IR2 is, right? Because IR2 has to be V12. See, this voltage V12 is also the voltage across the resistor, divided by R2 by Ohm's law, okay? Now, notice what happens. So we have an expression for the current going into the external circuit in both cases. It's I, and we have an expression for it. We can ask this very simple question, which is, in what case are those two circuits equivalent? When is that current the same? And I can set it equal and solve, and an interesting thing arises. If R1 equals R2, which is, I think, what you were alluding to, okay, and IS is equal to Vs over R1, or conversely, if Vs is equal to IS times R1, these two things do exactly the same thing. They're equivalent circuits.
And here's the important point to note about this. They are equivalent as far as the external circuit is concerned, which means we could use them as a black box. The external circuit, under all possible values of that external circuit, whatever load it applies, whether it's a headlight or a headlight and a car starting, we'll see exactly the same behavior.
That's right. So to this external circuit, no matter how big it is, it could be a microprocessor, it could be immensely complicated. When this external circuit electrically, from our perspective, looks out into through nodes 1 and 2 and down these branches, these two things, if you follow this equivalence, they'll be equivalent. They'll behave identically. And this has a particular use in solving circuits. Just let's do a bare bones example. You can see where this just has a practical application of how it helps you solve things.
So the example we're going to do is we're going to do an example where we'll solve a circuit using source transformation. Now, to give you some background information to show you why I would want to do it this way. You've already learned how to combine resistors in series and parallel and so on. So we can sometimes use source transformation to allow us to do these sorts of combinations very easily. So let's take a circuit. Here's a circuit that I'm giving you as an assignment, and I want you to tell me what the current is, I. And the current specifically that I'm looking for is the current that flows through this 3 ohm resistor here. Now if I look at this circuit, I see it has a current source, it has that parallel resistor over here, so this is a real current source, and then it has various other resistors. But none of them are easy to solve on their own because, well, this resistor RS1 is not in parallel with the 6 ohm resistor, so I can't combine it with that 6 ohm resistor. Let's see what I can do. What if I transform the current source and parallel resistor into a voltage source and series resistor using the math I just taught you? Well, if you do that, remember the resistor stays the same, so it's a 2 ohm resistor, but now the voltage source becomes a 32 volt source.
Oh, so you followed the rule we just gave them in the previous slide.
That's right, because a 16 amp current source driving into a 2 ohm load is a 32 volt voltage source driving through a 2 ohm resistor.
Okay, so the resistor stayed the same, so RS1 stays the same.
Correct.
And then we just modified, we came up with a voltage source to make them equivalent. I got it.
That's right.
Okay, that's pretty easy.
Now, look at the beauty of that. Now, my resistor ended up being in series with another resistor. So I know how to combine these. A 2 ohm resistor in series with a 6 ohm resistor is an 8 ohm resistor.
Right.
So I can then simplify to an 8 ohm resistor, and now I can transform back.
Oh, you did another transformation.
Exactly. I transformed back into a current source. So, but now what I had was an 8 ohm resistor, so it becomes an 8 ohm resistor in parallel. And to transform the voltage source into the current source, I take the 32 volt source and I divide it by 8, so I get a 4 amp current source.
So again, all you're doing is using those two little equations in the previous slide on the bottom left.
Exactly.
Okay, got it. Okay.
And now you'll notice I have an 8 ohm resistor in parallel with an 8 ohm resistor, so that's a 4 ohm resistor. So I have a 4 amp current source in parallel with a 4 ohm resistor.
Let me guess.
I'm going to transform.
Okay.
And I get a 16 volt source and a 4 ohm resistor in series with it. And now I have a straightforward loop, so I can figure out the current. The current is just going to be the voltage, 16 volts, divided by the series combination of all of these resistors. So it's 16 divided by 4 plus 1 plus 3, which is 16 divided by 8. So I now know my current, and that is 2 amps.
So one thing I wanted to point out that I noticed as you were talking, I've been asked before, if you look at this circuit, and this is just a very small detail, some students will say, wait, why did you start transforming from the left? You could have made the 1 and the 3 become a 4, and then the 4 and the 8 in parallel, and then put that in series with the 6 and so on. And that's all true. You could have collapsed the circuit this way, but then you would have lost what I is. Because what we were interested in doing is asking, what we wanted to solve is what the I through this branch is. So we needed to keep this part of the circuit intact, so to speak, and transform over from the left. So there's a little detail, but it's one that I've been asked a couple of times when students see this problem and are collapsing it. It's because the problem forces you to solve for I that we begin to transform from the left. Should we go on?
Yeah, let's go ahead.
So here's another type of transformation. And to motivate this, you know, by now, hopefully, you've done a few problems where you've collapsed resistors that are in parallel into an equivalent resistor, or resistors that are in series into an equivalent resistor, to aid you in solving things with KCL and KVL. But let's take a look at this circuit. And what I'm going to do is I'm going to ask you a question, and then we're both going to be quiet for just a few seconds. Just looking at this circuit, do you see any resistors that you could simplify by parallel or series transformations? So Vivek, what do you think?
Well, I kind of know this problem, but I think the answer is if I look at the circuit, there's no single pair of resistors that I could pick that I can say are in series. or in parallel. So for example, if I look at R1 and R4, well, I want to call them kind of in series, but there's R3 sticking over here, so that clearly doesn't work. Similarly, I could say, well, maybe I want to say R1 and R2 are in parallel, but they're not really because there's R3 in between.
And so that's exactly what this is all about. There are structures like this, and in particular, there's two structures that come out of circuits like this that we have transformations for to make it easier to solve this. So one of these structures is called a Y. And so you can see here, you can think about it essentially in a case where there are three branches with resistors coming off of a node. And think of it as a Y if I were come in from R3 and then I branch off into two other resistors, R1 and R4. So there's a Y right here. And it doesn't look like a Y because we've got them sort of flipped, but you can imagine drawing this as a Y, and you'll see that in a second on the next slide. And we also have a Y right here. It's the same thing. It's just symmetric. There's a Y formed by R3 feeding into R2 and R5, or you can think about it as R5 coming up, and then there's a Y formed by R3, R2, and so on. There's also a delta. And a delta is essentially a triangle of resistors. There's three nodes, and there's resistors between the three nodes. Now, notice that in both cases, the Y and the delta, we're dealing with three nodes and three resistors. They're just arranged differently. And so the trick here is going to be, can we transform Ys into deltas and deltas into Ys? And those are the two deltas I mentioned right here. So you have two deltas here. Okay? So let me, before giving over to Vivek here to work it out for you, let's just take a look at what we're basically a canonical Y. So here's a Y. We've got three nodes labeled 1, 2, 3, and the three resistors between those nodes R1, R2, and R3. And there's a common node in the middle. All right, take it away.
So the common node that Michel mentioned is the node 3, is the node C in the center. And we had three nodes, 1, 2, and 3. Let's say I were to give you this Y and ask you to figure out the resistance between node 1 and node 2, and I told you to assume for now that node 3 was disconnected, so it wasn't connected to anything. Well, now this is pretty straightforward because it really simplifies to a series combination of R1 and R2.
Now hang on, let me make sure I understand this. The reason that R1 plus R2 is the R1 R2 resistance is because there's no current going down R3. And that's because you said node 3 is connected to nothing.
Exactly.
Okay.
I have intentionally disconnected node 3, in which case I can ignore R3 because there's no current coming down here, and all I'm left with is current going from R1, from node 1 to node 2, right. So that's R1 plus R2. Current
going down R1, all of that current must go through R2 because it dead ends on node 3. Okay, got it. Got it.
All right. Now, let's say I give you a delta, and again I'll assume node 3 is disconnected. Now what this means is any current coming down RB must go up through RA. So RB and RA are in series, right. And that series combination is in parallel with RC.
Oh, I see. And this is this expression that you've got here. It's just basically all you're saying is RB plus RA in series in parallel with RC. Got it.
Correct. So remember, a series combination is RA plus RB. The parallel combination is RC in parallel with those. So we've got R12 is then this equation over here.
Perfect.
Now, you know what the next step is. The next step is to establish equivalence. For them to be equivalent, the Y calculation must be the same. It must give the same value as the delta calculation. In other words, R1 plus R2, which comes from the Y calculation, must equal to the part that came from the delta calculation that's shown over there. And we can do that for the other combinations of nodes. We can do that for nodes 1 and 3 and nodes 2 and 3, and we end up with these equations here.
So, okay, so we've got three equations and three unknowns depending on what we know is what you're saying. So, for example, and we'll move on to this in the next slide, but if I'm given a Y such that I know R1, R2, and R3, I know the values, then those would be knowns in these three equations you've got on the right side of the slide. And I would have three equations with three unknowns, and those unknowns would be A, B, and C.
Exactly.
Okay, so I guess to summarize all of that, here we go. This is the summary slide you'd use when reviewing all this. If I'm going from a Y to a delta, right, or a delta to a Y, I can use these equations and I clean them up depending on what I want to solve for. So let's say I've got a delta and I want to go to a Y. I know A, B, and C. I know the values of those things. And so solving those equations that Vivek wrote for you in the past, in the slide before, you arrive at these solutions, that R1 equals this, R2 equals this, and R3 equals that. We're not going to do that simplification for you. It's just basic algebra. And likewise, if I'm going from y to delta, I know 1, 2, and 3, what I'm solving for is a, b, and c. So I rearrange those equations to solve for a, b, and c. And I get that a is a combination of R1, R2, and R3, and likewise B, and likewise C. And a trivial thing you can also do for quick practice is asking what happens when they're all the same value. And you can just tell by symmetry that these will all collapse into one answer. But we'll leave that to you to figure out because it's pretty easy. Now, we'll do an example in a minute, but basically this transformation is very useful when you get these types of circuit topologies coming up and you think that going from y to delta would simplify your solution to the problem. And I think Vivek's going to show you an example of that right now.
That's right. Let's take a circuit, and this is an example circuit where I want to determine the current going through the circuit I. And I'm going to solve this using a y-delta transformation. And you'll see how using a y-delta transformation allows me to get to a circuit that I know how to deal with. So here's my original circuit. And you can see that I have no single series of parallel combinations that I can deal with. So this is a good candidate for a y-delta transform. And I want to determine the current I. So note specifically, if I look at nodes 1, 3, and 4, here's a delta. You see that there's a delta over here. So what I'm going to do is I'm going to do a transform on that delta. And I'm going to transform this delta into a y. So I'm taking the three resistors that form the delta between nodes 1, 3, and 4 and transforming it into a y. So now you see that I have a y between nodes 1, 3, and 4.
Okay, I see.
So I transformed a delta into a y. Now I look at the circuit, and what can you say, Michel? Do you think this is something you could solve?
Yeah, I think so, right? Because now, let's say the two resistors on the left, R3 and the 6 ohm below it, around node 3, those things are in series.
Correct.
And on the right branch, going down, say, from C to 4 to 2, R2 and the 20 ohm resistor are also in series. So it should be pretty straightforward to get equivalent resistors for those two. Should be 12 on the left and 24 on the right. And then put those in parallel, give me one resistor, and then again in series with the R1. So let's see, am I barking up the right solution? I think I am, right?
You are, because what we basically do is as Michel said, you end up with a 12 ohm resistor here, a 24 ohm resistor here. Then you can put those in parallel with each other and then put them in series with the 5 ohm resistor and the 12 ohm resistor. So then you end up with 25 total. So 12 and 24 in parallel gives you 8. 8 plus 12 is 20, plus 5 is 25. So you now know that you have this 100 volt source driving a 25 ohm net resistance. So you can get your net current is 4 amps.
Right. Because after all we wanted was the current down the total, which really makes it easier just to get rid of all these deltas and y's and collapse it. Now, let me ask you a question. You could have modified the delta that goes from node 2 to 3 to 4 and probably done the same thing.
I could have.
Okay.
That's right. So this is an important point. In all the circuits that we do, there are often multiple different ways to analyze them. And we're just giving you the tools right now to be able to analyze them. In the next few sections, we'll start giving you specifics on how to decide how to do the analysis.
The other thing I wanted to point out, I remember when I was a student, I was reading about Y deltas. I mean, it seemed like a neat trick and so on. But I never quite understood why it was such a big deal. And then I realized much later in life that Y delta circuits actually play a pretty fundamental role in power distribution and power generation, right? I mean, it turns out we don't have to go into it in detail, but there really is a very practical use for these kind of circuits in the way the way we generate power and then redistribute it at home.
That's right. In fact, if you look at the way the generation components in the grid and our household loads are set up, it actually has a lot of similarities to this.
Yeah. So those of you out there thinking this is just kind of a little trick we're teaching you, it is that, but it also has very, very fundamental practical applications for electrical engineers.